Hi, we're Team 1, and this is our project for the spring semester of Embedded Systems. The goal of our project is to be a vaccine distribution system. This autonomous system will be placed in a 10 by 10 playing field with 1 pickup and 3 drop-offs in 4 corners. The components in our system contain sensors, a robotic arm, navigation, and a tri-rover. Due to COVID constraints, the Pixy couldn't be in the final product, but here is the integrated demonstration. First will be the arm integration. Next we have the Rover with the LiDAR and the navigation commands.
Now we'll be talking about our team's sensor component. The sensor we used was a TF Mini Plus LiDAR. This was attached on top of the rover in the front. We primarily used this sensor to detect the distance between the rover and either the pickup location or drop-off locations. The TF Mini Plus utilizes the time of flight principle, and its distance readings are calculated by this formula on the right. It uses UART to communicate with the board and transmit data through an 8-byte frame. The first 2 bytes are 2 header bytes. Bytes 2 and 3 are the distance readings. Bytes 4 and 5 are the strength readings. Bytes 6 and 7 are temperature, and the last byte is a checksum. In order to get the distance, you need to left shift the higher byte and then add the lower byte to it. A struct is used to hold all the data readings from the sensor, and it's filled using a state machine. It is then sent to a separate thread to publish the data and process it to include things like average temperature readings or average strength or the average distance. Here is the JSON that is used to publish the data. We have the current distance and current strength, which means the distance and strength readings of the latest data sent, the average distance and strength, and then how many readings were sent in that time period. For testing, I used the logic analyzer and hooked up the TX of the LiDAR to the logic analyzer so I could see the bytes that were being outputted. As you can see here, we have the 2 header bytes, which will always be 59, and then the rest of the data. I also made a spec sheet of the sensor readings to test the accuracy. The LiDAR data was published to the MQTT server every 500 milliseconds, and this is based off a timer 500 callback. After making the spec sheet, I found that the readings from the sensor were accurate within plus or minus 5 centimeters of the actual marked distance. The state machine ensures that even if the data becomes out of order at some point, it can always go back, since the first 2 bytes are always checked to be the header bytes, which were specified to be 59 hexadecimal. One downside of this sensor was that since it was pretty small, the field of vision was pretty small too, and that meant that the objects that it was detecting needed to be pretty straightforward in front of it, or else it wouldn't be able to pick it up. Another downside was that anything closer than 10 centimeters would be unreliable, since most of the time it would just be detected as 0 centimeters.
I will now be showing a demo of the TF Mini Plus. This distance right now is about 20 centimeters, and as you can see on the reading, it's about 17, 18 centimeters right now, which is within the plus or minus 5 centimeters. And as I move the box back, the distance increases, and if I keep moving it, and if I bring it closer, the distance readings get smaller.
Hello, my name is McFeeters, and I was the ARM component engineer for Team 1. The ARM operated by placing vaccine payloads on the rover at the fixed pickup location on which it was mounted. Pulse width modulation was used to control servos of 4 joints, allowing for 4 degrees of freedom. The ARM was designed with 5 threads in a multi-threaded real-time operating system. These 5 tasks were responsible for publishing MQTT messages, high and low level ARM control, respectively, sensor readings, and statistics. The high-level ARM task made use of a struct of an anonymous union, pictured below, for receiving data of different types. The API for the ARM was implemented such that the ARM autonomously and independently monitored the navigation command topic for Team 1 and triggered action when a combination of conditions were met. These conditions, shown here as the rover state being stopped, the navigation command being set to stop, and the overall state is at pickup, represent the rover waiting for the ARM to supply a payload. The num drop-off value was also used to determine which payload to deliver. The constraints for the ARM included that it needed to be able to operate autonomously without external decision-making. It achieved this by parsing the navigation commands and using these values in the high-level ARM finite state machine. All the decision-making for the ARM was contained and executed on the TI board. In testing, I was able to set servos to specific angle values individually via one of the union types mentioned previously. The statistics task also provided a host of debugging capabilities for narrowing down issues by topic, task, and even to individual functions in the code. For reliability and robustness, the ARM moved smoothly between target positions, but it did have issues with the power bank automatically switching off if the ARM servos were not moving for a long enough period of time, due to the low current draw. I used male pin headers to prevent poor connection to servos while the ARM was moving. Those are shown on the right side. Manual ARM commands were also not processed until the current ARM action was completed, which resulted in unexpected behavior if another command was sent while it was still moving.
Hi, I'm Shania and I worked on the Pixy. The Pixy is responsible for detecting colors in the playing field. This was used if the rover is near a drop-off or a pickup. The communication method used was SPY, as it was the fastest communication offered by the Pixy. There were two threads used for the Pixy, a timer thread and a SPY thread. This is so that the SPY callback can be called in a timely manner. Every second, the SPY thread publishes into the MQTT on any color detection by the Pixy. So this is what would be published into the Pixy topic every second. So the Pixy was set to either detect no color, a green drop-off, or a blue pickup. Each color state was set in Pixymon, a program provided by Pixy, and published into the topic as well. So 1 would be no color, 2 is green, and 3 is blue. So as you can see by this Pixy demonstration, the color state is none, with the color signature of 1. And then now that the green object is in front of it, the color state updates to green, as well as the color signature 2. We take that green out, it updates back to the previous state. So now we will put blue, and that updates accordingly as well. And then it will go back to none again. So the Pixy was able to continuously upload camera data for up to an hour. The most accurate distance that it could detect color was around 15 centimeters with a plus or 3 minus error. One of the main issues that the Pixy had was the lighting has to be constant to detect the same colors. If it's not, then you would either have to set them on Pixymon again, or the colors won't be detected at all. I will now go over the navigation component. The navigation is responsible for sending nav commands to the rover in order to reach the pickup and drop off while avoiding obstacles along the way. The inputs would be the TF Mini LiDAR and PixyCam as mentioned before, and the outputs would be rover and ARM commands. The rover follows a path to the drop-off, and each movement is saved onto a stack. So once the rover is able to drop the vaccine, we look into that stack and able to head back to the pickup. The rover adjusts itself for ARM to place the next vaccine, and the process repeats until there's no more vaccines to deliver. Here's the navigation API that would be published in MQTT. The rover state, whether it's moving, turning, or stopped at the moment. The navigation command, move forward, turn left 5, turn right 5, turn around swing for the rover to follow, and this will be get more into detail later. The overall state for the ARM to know that we are at the pickup for the next vaccine or at the drop-off so the server can swing. And the number drop-offs is an int to signify how many drop-offs that we have reached. Python script using the TK library was used to imitate the playing field. As you can see, the rover reaches the drop-off, drops the vaccine, turns around to pick up 3 times for each corner. For each movement, it is uploaded to the MQTT topic, so as it's getting uploaded, the red circle moves accordingly. As seen by the Python GUI and the integration demo, the rover was able to reach the drop-offs from the pickup station and vice versa. Even though the Pixy wasn't in the full integration, we were still able to do a full live demo where the rover can move, swing, and tell the arm it's ready for the next vaccine.
I'm James Heiman, and I was in charge of the Rover component. The Rover component was responsible for movement of the system. It delivered and picked up the blocks and took them to the drop-off locations and went back to the pickup location. It provided an API for the navigation component to use, and which I'll get into later, and it utilized the PID algorithm to set the speeds, which I'll also get into later. As you can see on the right, this is the final setup that the rover had, with the LiDAR sensor in front, and then the servo on the left, which would use to drop off the blocks once it got to the drop-off point. So the rover was accessed over the API. The Rover API was accessed over MQTT, which is an online message queue software, and then a thread was created for each of the following tasks: receiving MQTT messages, publishing MQTT messages, sending to the motor controllers using the Siren 10 motor controller, as you can see on the bottom right here, reading from the motor encoders, which told you the motor speed, running the PID algorithm, and running API commands. So the Rover API provided 5 commands for navigation and control rover movement. Had move forward, move the rover 10 centimeters forward, turn left or turn right 5, which turned the rover 5 degrees in either direction, turn around, which turned the rover 180 degrees around, and swing, which swung the servo and to drop off the block once it got to the drop-off point. The PID algorithm ran this equation right here. So the error was calculated from the desired result minus the actual result, and the error was the integral of that was taken, as well as the derivative, in order to get the change to get the desired result and keep that desired result. So for the purpose of this, KD was set to 0, and KP and KI were determined through extensive experimentation of rover speeds. So for testing this, the rover actually had both an input and output specifically for debugging, where you could just set the motor speeds manually and read them as well. As you can see on the right, here is a GIF of the plot that of a plot of the motor values after they're set to 40. So you would in this case, you set the motors to a specific value, and then you just plot the encoder readings. And here, as you can see, it starts at 0 and it goes to 40, much like a PID curve would. Ideally speaking, you would plot the expected value versus the actual readings, but as you can see here, it bottoms out at 40. And, it's pretty obvious what the expected result is. So as for reliability and robustness, the rover was successfully able to run the entire duration of the final demo and more without issue. It could run for several hours with no issue, as long as the hardware seems to be good and the Wi-Fi seems to be good. The rover is also robust against bad navigation commands. It stops when it receives a bad command, and if it doesn't receive enough commands, it doesn't do anything, it just stops. As for the margins of error for the different movements, for move forward, it has a margin of error of 15%, and then the turning has a margin of error of 20%. However, turnaround only has 5.5%. So the more commands that you send, the less the margin of error generally is, because it usually cancels out one way or the other.